Hello, my dear students. Welcome back to Shlokas Academy YouTube channel. In the last session, we have discussed atomic models and we have finished Thomson's atomic model, and we have also discussed about Rutherford's atomic model. In the Rutherford's atomic model, up to the definition of the nucleus we have done. Now, after the completion of Rutherford Goldfile experiment, and here in this session, today we are going to discuss about results of Rutherford's Goldfile experiment. And what are the results? Right. So here we have three important results. The first one, calculation of radius of any nucleus, means how to calculate radius of nucleus or radius of atom. Second one, whenever Rutherford was doing alpha scattering experiment, so there are three types of alpha particles that already we have discussed in the Rutherford atomic model. They are, the first type is that which are most of the 99.9% of the alpha particle passing through the Goldfile without any deflection. This is one type. Means most of the 99.9% of these alpha particles are passing straight towards through Goldfile without any deflection. This is first type. And second type, few alpha particles, right, get deflected through small angles, very few. And out of 20,000, only one alpha particle will get back on its original path. That means it is suffering from 180 degrees of deflection angle. So here total how many types of alpha particles are there? 3. Now the second result was that number of alpha particles that are scattering at any angle theta, how it is related with angle. Means, for example, if the angle of deflection is very high, what about the related alpha particles which can deflect through that particular angle? It is very less. The relationship between them, that can be explained in the result too. Third result, that is very important for advanced point of view, IIT advanced, and there was some questions in advanced examinations also, right? So that is distance of closest approach. Means in this we are going to discuss about three important results: calculation of radius, scattering of alpha particle, how they related with an angle of deflection. Third, distance of closest approach to the approach of the alpha particle. These three we will discuss one by one. First, let me discuss one by one. The first I am going to discuss calculation of radius. Calculation of radius of any nucleus. Right? One by one I will discuss. Calculation of radius means, according to Rutherford's atomic model from his experiment, he concluded that volume of the atom, any atom you take, if the volume of the atom, first radius of the atom is, right, 10 to the power of minus 8 centimeters. Then the radius of the nucleus is 10 to the power of minus 13 centimeters. In some books, they also given in the same value in the meters, right? So atom, according to Rutherford, atom is to be considered as a sphere. Sphere means, now if you know the radius of the sphere, how to find out the volume of the sphere? So we have the formula, volume of the atom or volume of the sphere is equal to 4 by 3 pi r cube. Here r is the radius of the atom, which already we know. If I substitute this r value in this, right, I can write volume of atom equal to 4 by 3 into pi into 10 to the power of minus 24 cm cube, centimeter cube. And here similarly volume of the nucleus volume of the nucleus is equal to 4 by 3 pi into 10 to the power of minus 39 cm cube. Means this is the volume of the atom and this is the volume of the nucleus. From these two, I can compare how big the atom is compared to its nucleus. How big as compared to the nucleus of the atom. For example, from this, I can write volume of atom by volume of nucleus equal to what I can write 4 by 3 pi into 10 to the power of minus 24 cm cube by 4 by 3 pi 10 to the power of minus 39 cm cube. If I get cancel these two, then I will get 10 to the power of 15. Means as compared to the volume of the nucleus, the volume of atom is 10 to the power of 15 times bigger. You just imagine how big the atom is as compared to the nucleus. For an example, if you consider the football stadium as one atom, the football present exactly at the center of the atom can be a nucleus, right? So from this, I can write volume of atom is equal to 10 to the power of 15 times the volume of nucleus. Means as compared to the nucleus volume, the volume of the atom is 10 to the power of 15 times more. It is a very bigger as compared to the volume of the nucleus. This is how we can compare the volume of atom and volume of the radius. This is okay. Here we are able to compare the volumes of atom with its nucleus. But how to calculate the volume of any nucleus of any atom? So for that also he has given one formula. What is that formula? I will explain. Listen to me. Right. First, volume of any radius. Volume of any nucleus. Nucleus or radius. Radius of any nucleus, that is given by R is equal to R naught into A power 1 by 3. Here R is the radius of nucleus whose radius is to be found out, and R naught is a constant. What is that? R naught is constant whose value lies in between 1.1 into 10 to the power of minus 13 centimeters to 1.44 into 10 to the power of minus 13 centimeters. Right? If they are not given any of these values, by default, the R naught value should be taken as 1.33 into 10 to the power of minus 13 centimeter, the most common value of R naught. Right? And here the A is mass number of the atom. Mass number of the atom. Right, that may be number of protons plus neutrons present in the nucleus. So this is what, by using this formula, Rutherford have explained how to find out the nucleus of any atom, the radius of any nucleus for any atom. Next, this is once again we will recall about first result. Result one is what? Calculation of radius. How to calculate the radius? We will discuss. Calculation of radius. Already we have done. Once again, we will recall this one. Right. Calculation of radius. According to Rutherford atomic model, radius of any atom is 10 to the power of minus 8 centimeter. The same value, if you express in meters, that could be 10 to the power of minus 10 meters. Next, radius of nucleus, which is equal to 10 to the power of minus 13 centimeter. If you express the same value in meters, that could be 10 to the power of minus 15 meters. As atom is sphere, I can calculate the volume of the atom as 4 by 3 pi r cube. If you substitute the R value here, you will get volume of the atom as 10 to the power of minus 24. 4 by 3 into 10 to the power of minus 24 centimeter cube. Similarly, volume of the nucleus, already we know radius, and if you substitute here 10 to the power of minus 13 power 3, right? 13, it was missed here, please note down it. It was 13 here. 10 to the power of minus 13 power. 10 to the power of minus 13 power 3. Right. So equal to, here this is the volume of the nucleus. It is not atom, it is nucleus. Now compare these two values. Volume of atom is equal to 10 to the power of 15 times the volume of the nucleus. This is how the Rutherford had compared the volume of atom with its nucleus, and he has proved that the volume of atom is being 10 to the power of 15 times larger as compared to its nucleus volume. Right. Next, we should discuss about radius of any nucleus. Any nucleus is given by this formula. What is the formula? R is equal to R naught into A power 1 by 3. What is R here? The radius of the nucleus, whose radius is to be find out. That radius we have to find out. And R naught is a constant, and whose value lies in between 1.1 into 10 to the power of minus 13 to 1.44 into 10 to the power of minus 13. But most common value of R is what? By default, if nothing is given, you can consider it as 1.33 into 10 to the power of minus 31. And what is A? A is mass number, right? Let me explain one example for the calculation of this radius or volume, anything. If you know the volume, obviously you can calculate the radius also, right? Calculate the radius of nucleus of aluminum. How do you represent aluminum atom? It's atomic number 13. It's a mass number 27. Now, what is the formula according to Rutherford? R is equal to R naught into A power 1 by 3. Here, this R we should find out. Radius of aluminum nucleus is equal to radius R naught value. Nothing is given in the question, means by default what we should take? R naught is equal to 1.33 into 10 to the power of minus 13 centimeters should be taken or not. So here I am taking the same 1.33 into 10 to the power of minus 13 centimeters, right? So this is R naught value into, what is the mass number of the aluminum? 27. 27 power 1 by 3, right? Now radius of aluminum nucleus is equal to 1.33 into 10 to the power of minus 13 centimeter into 27. I can write 3 power 3 whole power 1 by 3. Here 3 get cancelled. So radius of aluminum I can get 4 into 10 to the power of minus 13 centimeters. This is how we can find out the radius of nucleus of any atom. Understood? All of you note down this problem as example and the solution also. Now, result 2, the second result we have to discuss. What is the second result here? Already I told. So, in the alpha particles, there are 3 types of alpha particle. In the experiment, we have found that there are 3 types of alpha particles. What are those 3 types? Already I have told. One is the alpha particle which are passing through the gold foil without any deflection, right? And another one is the alpha particles which are showing some deflection from their path. And the third one, very few, that is out of 20,000, only one alpha particle, right, which comes back on the same path. Now here, number of alpha particles scattered at any angle theta is inversely proportional to 4th power of sine theta by 2. 4th power of sine theta by 2. That means if higher is the deflection angle, lower will be the number of alpha particles which are deflecting through that particular angle. For an example, most of the alpha particle, I said, most of the alpha particles are passing through gold foil straightly without any deflection. Means here, what is the angle of deflection? That was 0. That means lower is the angle, higher is the number of alpha particles. And very few alpha particles are getting deflected through small angle. Means theta from 0 to, for example, it has come up to 45 degrees. Number of alpha particle decreased from 99.9% to it is very few. Right. And the only one out of 20,000, only one is coming back on its original path. Means what is the theta value here? 180. So that is given by Rutherford experiment, result 2. What is result 2 means here? Number of alpha particles scattered at any angle theta is inversely proportional to 4th power of sine theta by 2. So mathematically I can write n theta means number of alpha particles scattered at any angle theta is directly proportional to, right, sine theta by 2. Sorry, I made a mistake here. It is not directly proportional, inversely. I'm writing here n theta is directly proportional to 1 by sine theta by 2 whole power 4. This is not correct. See here, as the theta value increases, what about this n theta decreases? As the theta value decreases, what about n theta increases? So that was concluded by the Rutherford as higher is the angle, lesser will be the alpha particles, and vice versa. Means if lesser is the angle, more will be the alpha particle. This is about result 2, right? And result 3, very, very important, that is distance of closest approach of alpha particle. Distance of closest approach of alpha particle. As we discussed, there are 3 types of alpha particles. What are those 3? Those which can pass straightly through gold foil without any deflection. They are very huge number and they are moving away from the nucleus. That is why they are not at all getting any deflection. And the second is that few alpha particles which got deflected through small angles. That means these are slightly moving closer towards the nucleus. Out of 20,000, only one alpha particle get deflected by an angle of 180 degrees deflection angle. That means that is only the one alpha particle among 20,000 which is moving straightly towards the nucleus. That is the reason it got more deflection compared to all. Right? Means the distance of closest approach of alpha particle is applicable only for those alpha particles which are moving straightly towards the nucleus. It is not all, right? So what is this distance of closest approach, right? The distance of closest approach, it is applicable only for those alpha particles which are traveling straight towards the nucleus. That means the particles which are returning back to their original path. The distance of closest approach is only applicable for those particles which are returning back on their original path, means who are getting at 180 degrees angle of deflection. Very important. So how it will, I will explain. Listen, concentrate here, and very important it is how I will explain. Here I am taking, this is point A and this is point B. This is nucleus of any atom. So being an atom, it should have atomic number. The atomic number or the charge present on the nucleus is Q1, which is equal to Ze. Z is atomic number, E is charge on the each proton. Charge on the each proton. What is Z? Z is atomic number here. That is very important. Atomic number, and E is charge on each proton. Charge on proton. Because in the nucleus, the charged one is only proton, not neutron. Neutron is a chargeless, right? Next, this is Q1. The charge on the overall charge on the nucleus, I am taking it as Q1. So towards this nucleus, from a distance of infinity, from infinite distance, I am throwing an alpha particle. What I am throwing? Alpha particle. What is meant by alpha particle? Alpha particle is nothing but a doubly ionized helium particle. In the previous video, I have already discussed. Doubly ionized helium particle is called as alpha. Means what is the charge on alpha? Charge on alpha is 2e and mass of alpha 4 AMU. And this alpha particle is throwing or projecting towards the nucleus from an infinite distance. Infinite distance. So at point A, let the charge on the alpha particle be Q2, which is equal to 2e. This is also positive charge. It is also positive charge. Right. And what is the mass of alpha particle, which is 4 AMU? We know that 1 AMU is equal to 1.66 into 1 AMU. 1 AMU is equal to 1.66 into 10 to the power of minus 24 grams. If you want, you can substitute this one also, right? Mass and alpha. You are throwing from a large distance and it should possess some velocity. I am taking it as velocity as V alpha. I don't know that. It is unknown. This is Q1, Q2, and M alpha are known, but V alpha or velocity of alpha particle is unknown. Right. Now it is throwing, means projecting towards the nucleus. Now here, tell me one thing. Can the alpha particle touches the nucleus? No. Why? Alpha particle is having positive charge. The nucleus also having positive charge. Both are positive charge. Positive charge, positive charge. We have discussed in the properties of charge. Like charges repel, opposite charges attract. These are the two opposite charges which repel. So that it come up to point B, from point B it returning back on its original path. Means at point B, what will be the velocity of alpha particle? It becomes 0. And the rest of the things are all are same. Now the distance between from point B to point nucleus is called as R minimum. This distance we have to find out. R minimum, or I can also take it as R naught, distance of closest approach. This distance is called as closest approach. Now we have to find out. Right. At point A, I am taking at point A, what I can take here, potential energy according to properties of charge. If you want, you refer back properties of charge notes, right? Potential energy when Q1, Q2 are two charges and they are separated by a distance R, then their potential energy is equal to potential energy at point, right? A is equal to K into Q1, Q2 by R. Here, what is R? Infinity. From point A to nucleus, the R is infinity or not? So then I can write at point A, the potential energy will be 0 because R is equal to infinity. Something by infinity, always it is infinity. It is potential energy. Then what about kinetic energy? Kinetic energy is equal to at point A only. Right, I can write half m alpha v alpha square. So this is not equal to 0. Right. This is all about at point A and total energy at point A. Total energy means I can sum up potential and kinetic energy. So 0 plus half m alpha v alpha square. This is total energy that was obtained at point A. Now let us calculate the total energy at point B. At point B. Tell me, at point B, what is V alpha? It is 0. But here, the distance is finite, not infinite. So that at point B, the potential energy cannot be 0. I can write. So K into Q1, Q2 by R minimum or R naught, which we need to find out. And Ke will become 0 at point B. Why? V alpha is 0 of m into V alpha square. V alpha is 0. So Ke is equal to 0 because V alpha is 0 at point B. Now what is the total energy at point B? The total energy at point B equal to K into Q1, Q2 by R minimum. Now This is, let it be equation 1 and let it be equation 2. From 1 and 2, what we can conclude? Tell me. From 1 and 2, what we can conclude? From 1 and 2. From 1 and 2 and law of conservation of energy. Energy can neither be created nor be destroyed. Right. What we can write? Total energy at point A must be equal to total energy at point B. Right. What is the total energy at point A? Half into m alpha v alpha square.
Okay. From equation 1 and from equation 2, we can find out the formula to calculate distance of closest approach. From 1 and 2, right? I can write according to law of conservation of energy, according to law of conservation of energy, right? I can say total energy at point A, that is TEA, must be equal to total energy at point B. Now, what was the total energy at point A? This was half m alpha v alpha square. And what is the total energy at point B? This is K into Q1, Q2 by R minimum. So this is the formula to find out distance of closest approach of alpha particle towards any nucleus atom. Here the Q1 is the charge on the nucleus, that is Ze, Q2, all these things. And if you want to still modify, R minimum is equal to, you can write 2K Q1 Q2 by m alpha into v alpha square. This is the formula, and in this Q1 is equal to charge on the nucleus with atomic number. Z is the atomic number of the nuclei, right? So that we can find out. And Q2 is charge on the alpha particle, which is known, which is equal to 2e. And K is a constant. In CGS system, the K value 1 in CGS system. And it is 9 into 10 to the power of 9 in SI system. Already we have discussed in charge properties of charge, this one. And m alpha is mass of the alpha particle, which is 4 AMU. And 1 AMU is equal to 1.66 into 10 to the power of minus 24 grams. And V alpha, this is unknown, this will be given in the question. Velocity of alpha particle. Velocity of alpha particle. And R minimum is the distance of closest approach, which we should find out. Right. So next, limitations. Based on that formula, try to solve this question. The question is that when alpha particle is projected from infinity with velocity v naught towards the nucleus of gold atom, find out distance of closest approach, that is R minimum, velocity of alpha particle at a distance of 2 R naught from the nucleus, and what will be the speed. Try to solve this one. If you don't get, I will explain in the next video. And last, limitations of the Rutherford atomic model. It could not explain, it is T, that was printing mistake, it could not explain hydrogen spectrum. And according to classical law theory of electromagnetism proposed by Maxwell, if a charged particle is revolving around another charged particle, it will continuously lose energy. So the path of the electron around the nucleus should be spiral, not circular. And finally, electron will fall into the nucleus and the atom should be collapsed. That means atom should be unstable. But most of the atoms are being stable. why it was not explained by the Rutherford. These are the limitations, right? In the next video, we'll move on to the atomic number, mass number, isotope, isobars, isotherms, all isotherms. And after that, we will move on to the electromagnetic radiations, all these things. Right. Thank you for watching. Please subscribe Shlokas Academy YouTube channel and share. Thank you.